Chapter 16 is all about our sun. One of the important things to understand is the things that we learn about the sun throughout this chapter, we're going to apply to other stars, right? The sun obviously is our star, and it really is. We've had very, very close-up observations of the sun for quite a long time now. And that is going to be used to really help our understanding of other stars. And in fact, we will model other stars based on the sun, based on the amount of energy that comes off of the stars, the amount of mass the other stars have. We almost always will compare those other stars to the sun. So this is a very important chapter. I mean, all the chapters are important, obviously, but this is very important because we'll be using it to compare. All right, so let's see, what do we do? Okay, let's just move on. This is just the different topics. We're going to cover the basic properties, the interior of the sun. We can actually detect sound waves traveling across the sun. The solar atmosphere, what's called the photosphere, the chromosphere, and the solar corona. We'll talk about those things. The magnetic field, which leads to sunspots. How the sun is, how it's active. In other words, there are solar flares. There's what are called prominences, things like that. All right, and how those activities, these solar flares and things affect us on Earth. We'll talk about what goes on at the center of the sun. In fact, this is really important. The idea that really the power of stars happens at their center, or that they're calling it the heart of the sun. And we'll talk a little bit about the fundamental forces. The gravitation and the strong nuclear force. That's very important to understand how energy comes out of the sun. We'll talk about that. And then because it's a nuclear reaction, it creates these particles that are almost massless. And travel almost at the speed of light. They're called neutrinos. And the ones that come from the sun are called solar neutrinos, obviously. Well, I guess that's not obvious, but all right, let's get into it. So the properties of the sun. The sun is, it's almost 1 million miles across. Anyhow, its radius is 700,000 kilometers. The mass is the usual number that we use is 2 times 10 to the 30th kilograms. It's not exactly that. It's like 1.99 something. But that's the typical value that we'll use in astronomy. The density, so this is in kilograms per cubic meter. So this is 1400, obviously. Just to give you a sense, fresh liquid water has a density of 1,000 kilograms per cubic meter. Right? I don't really like kilograms per cubic meter when you talk about density. It's actually much more, for me anyway, it's much more natural to talk about grams per cubic centimeter. So, for example, liquid water has a density of 1 gram per cubic centimeter. Fresh water, it's got to be, not salt water is a little bit more dense. And, things like a rock that you pick up, on the ground, on the earth, on average has a density of about 3 grams per cubic centimeter. Our planet has a density of about 5.5 grams per cubic centimeter. You can look on the periodic table. You can find, for example, iron, like a solid piece of iron, has a density. I think it's somewhere between 7 and 8 grams per cubic centimeter. So just understand that the density of the sun has to do with what it's made of, which is primarily hydrogen and helium. And it's an enormous, this is a huge size. And then, as we explore the rest of as we start to explore our galaxy and even in other galaxies, we're going to find that this is not so big. It turns out our stars, and that's actually a good thing, because if our star was much bigger than it is, it would actually be towards the end of its life, which we don't want. And in fact, one of the things, I guess I should say something about that right now, is from our understanding of how stars evolve, we think that all evidence shows that our sun is about midway through its life cycle. Okay, so I guess that pointing out something else, that the stars are born, they live a long time our sun will live we think about 10 billion years, so it's been around 4.5 billion years, just like the Earth. The Earth and our star were born around the same time. Oops. All right. So anyhow, I'm getting a little off topic. So the density is a little bit more than that of liquid water, and primarily because it's made mostly of hydrogen and helium. It has what we call differential rotation, which just means that it doesn't rotate as a solid. It rotates at the equator. It rotates at a different rate than it does, at different latitudes. It's not a solid object at all. Of course, it's a ball of what we call plasma. Anyhow. What we generally do when we talk about the rotation rate is we'll look at sunspots and how long it takes certain sunspots to go all the way around. Although the sunspots don't necessarily last that long, so sometimes it's hard to tell exactly what the rotation rate is. The surface temperature, some textbooks you'll find that they'll call the surface temperature 6,000 Kelvin. Here, this is the actual, or very close to the actual number, the surface temperature of the sun. And the surface of the sun is called the photosphere, which is right here, right below that. So the actual surface of the sun is at 5,800 Kelvin, approximately. It's not exactly that number, but that's perfectly fine. We're gonna find that there are certainly other stars that are much hotter than this. There are other stars that are much cooler than this. In fact, the majority of stars in our galaxy are much cooler than this. They're M-class stars. We'll talk about that later. All right. So again, we're focusing in on the sun. You really have to filter. You can't obviously never look directly at the sun. I think you probably know that. But we have filters where we can even turn certain telescopes towards the sun and get information. Notice this here. You can actually see the sunspots. I've looked through many telescopes that have these solar filters. But you have to be careful. If you get like a relatively inexpensive telescope, I would very much research and make sure that solar filter is really good before you go pointing it at the sun, because ultimately you could blind yourself by even looking at the sun through a telescope in a very short amount of time. Notice they're showing here what's called the solar corona. That's the outer atmosphere. And for some reason, we think we know why, but think about the atmosphere of the Earth. If you are at the base of a mountain and you climb to the top of the mountain, even a mountain relatively, like North Carolina mountains or even some of the mountains in South Carolina, you climb, 3,000, 4,000, 5,000 feet or something like that. it feels cooler, right? So that really happens with our atmosphere. The further you get from the surface of our wonderful planet, the cooler it gets. And it's actually opposite that. Remember, the surface of the sun, which is also known as the photosphere, okay, and then there's a small thin little layer called the chromosphere. But what this is showing is this region called the solar corona. And the solar corona, remember that this, the actual surface, 5,800 Kelvin, this can be up to close to 1,000,000 Kelvin, and a little bit hotter than that sometimes too. All right, so anyhow, we'll explore how that happens, or at least how we think that happens. There's actually a spacecraft that was launched not too long ago. It's called the Parker Solar Probe, that is trying to figure out why one of its missions is to try to figure out why the solar corona is so hot, so much hotter than the surface of the sun. All right, so then let's get into the interior structure of the sun. Of course, we'll start at the core, right? This is actually where the action is, as far as the energy, where the energy of the sun. What is the energy source of the sun? Basically, what happens in the sun is similar, very, very similar to a hydrogen bomb. Humans made hydrogen bombs back in the 1950s, but this is, like the kind of hydrogen bomb we would never ever see on our planet. Our hydrogen bombs are nothing compared to what goes on in the core of the sun. But what's really taking place is hydrogen is turning into helium. It's getting squeezed together and turned into helium. We're going to explore that a little bit. But that's actually the source of energy of stars until they quote die, right? That's exactly. In fact, that's how when a star is born, hydrogen is the moment hydrogen is turned into helium. All right, so there's also this radiative zone, so that's where the photons pass through this region. It's somewhat less dense right here, and so the photons can pass through here until they reach the convective zone. And what happens is the convective zone is a little bit more dense, and so the photons of light get absorbed, and this material heats up. And convection is when hot material moves from place to place. And basically the material of the convective zone, receives the photons that originated from the core, usually gamma ray photons, by the way, but all frequencies as well. All wavelengths, I should say. And that's both. That's the same thing. All frequencies, all wavelengths. It's just a different way of looking at it. Anyhow, the photons will pass through the radiative zone of almost at the speed of light. They hit the convective zone and bounce around. They get absorbed. So the actual material bounces around more frequently in the convective zone. And, we've actually done statistical analysis on this where, a photon could be turned into heat and bounce around for many, many years in here before it actually reaches the surface of the sun. And so the actual surface of the sun, as this thing is pointing out, is called the photosphere. So that's the actual surface of the sun. And then there's a thin atmosphere above that called the chromosphere. Relatively thin, so it's 1,500 kilometers. I'm sorry, it's showing you where it is. So from where the photosphere is to the outer edge is 1,500 kilometers. So it's like a little shell, and then then there is the solar corona, which can extend up,